C2 and C3 are connected in series, the total capacitance C will be such that 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. Alright, let's see what happens if two capacitors, instead of connecting three, suppose if two capacitors are connected in series, what will be the total capacitance of that combination? Well, 1 over C will be equal to 1 over C1 plus 1 over C2. Can you simplify and solve for C from here? What will be C equal to? If you simplify this, C1, C2 is the common denominator and the numerator will be C2 plus C1. So simplifying this gives you C1 plus C2 on the numerator divided by C1 times C2. If 1 over C equal to C1 plus C2 over C1 C2, what is C equal to? C will be the reciprocal. C therefore equal to C1 C2 divided by C1 plus C2. When two capacitors of capacitances C1 and C2 are connected in series, the total capacitance of the combination C equal to C1 C2 divided by C1 plus C2. A very important relation. Now tell me if you know what that relation is. When capacitors are connected in series, will the total capacitance be greater or smaller than any of the capacitors we used here? What do you think? Well, take an example. Suppose I use C1 equal to 5 and C2 equal to 10. Alright? If C1 equal to 5 and C2 equal to 10, what will then C equal to? Let us say C1 equal to 5 microfarad. C1 is 5 microfarad and C2 is 10 microfarad. Then C will be equal to C1 times C2 will be 5 times 10, 50 divided by C1 plus C2 will be 15, and that will be approximately 3.33 microfarad. So when a 5 microfarad capacitor and a 10 microfarad capacitor are connected in series, the total capacitance of the system is C1 C2 divided by C1 plus C2, 50 divided by 15, that is 3.33 microfarad. The total capacitance is smaller than the smallest of the capacitors used. So tell me, what is the use in connecting capacitors in series? Why do you want to do that? Well, sometimes you may need a value of a capacitor that is not in your stock. You want a very small value of the capacitor that is not in your stock. You can obtain the desired value by connecting 2 or 3 or 4 high value capacitors in series to give you your desired value of the capacitance. So that is the idea of connecting capacitors in series. When capacitors are connected in series, the total value of the capacitance will be less than the smallest of the capacitors used in the circuit. Capacitors are connected in series when you need a smaller capacitor than the ones you already have. Let's do a problem. A 10 microfarad capacitor is connected in series with a 20 microfarad capacitor, and the system is connected across a 6-volt battery. Find the equivalent capacitance of the combination. B. What is the charge on each capacitor? And C. Find the potential difference across each capacitor. Well, that's not difficult. This is the situation. You have two capacitors, 10 microfarad and the other 20 microfarad in series, and the combination is connected to a 6-volt battery. Find the equivalent capacitance of the combination. Well, if C1 equal to 10 microfarad and C2 equal to 20 microfarad, what is the equivalent capacitance? The equivalent capacitance C will be C1 C2 divided by C1 plus C2. Now let me caution you, this equation can be used only if you have two capacitors. If you have three, you cannot extend this equation for that. This is useful only for two capacitors. So when you have two capacitors in series, the total capacitance is C1 C2 divided by C1 plus C2, and that will be C1 is 10 microfarad, C2 is 20 microfarad divided by 10 plus 20. What is that equal to? That will be 200 divided by 30. That will be 6.67 microfarad. You see, when capacitors are connected in series, the total capacitance will be smaller than the smallest of the two. The smallest of the two is 10. The total capacitance is less than that. So your total capacitance is 6.67 microfarad. What is the next thing we need to find? What is the charge on each capacitor? Well, in order to find the charge, you need to know the potential difference. Is that right? Well, the charge on C1 equal to the charge on C2 equal to the total charge. You see, when capacitors are connected in series, the total charge in the circuit and the charge on each capacitor will be the same, because it's the same charge that flows from one capacitor to the other. So the total charge will be the same as the charge on C1, will be the same as the charge on C2. Is there any way to find the total charge? Well, yes, there is a way. What is it? We know the total capacitance. We know the total voltage. Well, if you know the total capacitance and if you know the total voltage, can you find the total charge? Yes, Q equal to CV. Is that right? If Q is the total charge, then Q equal to CV, where C is the total capacitance and V is the total potential. The total potential is 6 volt and the total capacitance is 6.67 microfarad. Therefore, the total charge Q equal to 6.67 times 6 volt, that will be 40 microcoulomb. 40 microcoulomb is the total charge in the circuit, and each of the capacitors has the same amount of charge. So what is the charge on each capacitor? The answer is, the charge on each capacitor is 40 microcoulomb. Find the potential difference across each capacitor. Well, you know the charge on capacitor 1. How much is it? 40 microcoulomb. You know the capacitance of the first capacitor. Well, if you know the capacitance and the charge on the capacitor, can you find the potential difference across the plates of the capacitor? Yes. V equal to Q over C. Is that right? Yes. So V1 equal to Q1 over C1. Q1 is 40 microcoulomb. C1 is 10 microfarad. So that will be 40 divided by 10. That is 4 volt. The potential difference across the first capacitor is 4 volt. If you now understand the mechanism of a series connection, you could tell me the other one right away. What is the potential difference across the second capacitor? Well, the total potential is divided. The potential difference across the first capacitor plus the potential difference across the second capacitor must be equal to the total potential. So the total potential is 6 volt. The potential across the first capacitor is 4 volt. So what must be the potential across the other capacitor? It must be 6 minus 4, that is 2 volts. Well, we can find the same answer by going this way. If V1 equal to Q1 over C1, then V2 must be equal to Q2 divided by C2. There you are. And Q2 is the same as Q1, is the same as the total charge. So Q2 is 40 microcoulomb, C2 is 20 microfarad. That will be 40 divided by 20 is 2 volts. You can see here the total potential across the two capacitors equal to the total potential provided by the battery. Okay, well, I'm going to make this a small lesson, and the next part is capacitors connected in parallel. I'm going to get back to you with that lesson a little later.